Hello, I'm Václav Novotný and welcome to the tutorial of Decentralized Systems 1. This tutorial will be focused on energy storage systems and diagrams for load demand which are used for sizing of energy resources. So in this tutorial we will have a look at thermal energy storage and storage of electricity. So let's start with the thermal energy storage, which we can classify based on the range of scales like temperature level, basically from storing cold to let's say about in negative temperatures like -20, -50, up to storing heat in temperatures more than 500 degrees C. Then the scale of size, whether it's for, let's say, domestic application in order of dozens of kilowatt hours, or if it's large scale grid size application. Then, of course, nature of heat supply and demand, or speed and number of cycles. The applications for thermal energy storage can be either for heating demand, or the heat can be stored for subsequent power production in thermodynamic cycle. You can see that the range of possibilities of the storage type are rather large. As you can see, we can have, for example, solid beds of some rocks or different material. We can have also particles with some particle handling system, solid monoliths. We can have liquids either as molten salts or for low temperature water. Also we can use organic fluids as oils or antifreeze for negative temperatures. And then there are methods for example, physical bonds like absorption-adsorption, or chemical bonds for thermochemical conversions. And except for storing the sensible heat, we can also store the latent heat, which are the phase change material abbreviated as PCM. And in this PCM, it's the heat of phase change like evaporation, condensation, or heat of melting that stores the thermal energy. Here let's have a look at different conceptual technologies. Here they are shown on example of storing high temperature heat from concentrated solar power plants, where on the first figure A, over here, we have some receptor for the heat, and then the heat is directly transferred into some fluid which is stored in the hot tank when we want to store the heat, and then it's pumped from the hot tank over the steam generator for the turbine to the cold tank, where it stays until we have time of available heat to again pump the fluid from cold tank through the heat source back to the hot tank. Then, as you can see on the figure B, the accumulation, the hot and cold tank, can be from different materials or using different fluid than is in the main circuit, and they can be then separated by a heat exchanger. Other option is that we don't have two separate tanks, but we have single tank with very sharp stratification between the hot and cold fluids, so-called thermocline. And here on the last figure we can see a solid block for energy storage, here particular concrete storage, where the hot fluid can flow through channels in this solid block and so charge it, and then during this charging a separate pump would pump the cold fluid through the storage, get the hot fluid, which then goes to transfer the heat in the boiler in the steam generator. The two-tank system is illustratively also shown here, where we have some heat source either as solar thermal collectors or in parallel when the sun is not available, so natural gas boiler. Then the heat goes into the hot tank when the heat is needed, so it's transferred from hot tank to cold tank via heat exchanger, which transfers the heat for further utilization. So in this slide you can see different options of seasonal thermal energy storage, where the one option is large water tanks built typically under neighborhoods of several houses. Some things like this can be seen as pilot applications, for example in Denmark or perhaps Switzerland. And this heat is typically not at very high temperature, so it is used mainly to partly heat up the return water before it goes to the boiler or before it goes to the heat pump. Other option than having a large water tank is using aquifer, where we inject the high temperature heat, or high temperature in this case, let's say about 30-40 degrees C in summer from typically some large solar collector arrays. So we inject this heat into the aquifer, into the borehole in the ground, and then in winter we can also inject the cold, so that we have the heat stored for the winter and cold stored for summer. Other option is to drill multiple boreholes, and also again in summer store the high temperature or higher temperature heat from some solar collector arrays, and then in winter use this for the source of, for example, heat pump. And while in summer we are storing this heat, so the cold water which is pumped up can be used, for example, also for air conditioning. Now the basic principles of the storage of the heat storage in liquid forms is two tank storage, which is illustrated over here. We have some heat source, hot tank and cold tank. So when the storage system is discharged, so that means the cold tank is full, and then when the heat is available, so from the cold tank it's pumped through by the pump via heat source, where it heats up and is stored in the hot tank. Then if the hot tank would be cooling down, so we have also option of some recirculation to keep up the temperature. And when the heat is needed, so the fluid is pumped from the hot tank to some heat exchanger or directly for heat utilization. The advantage of this system is that in the tanks, if we exclude any losses, so the temperatures are constant, and both the heat source heat exchanger and heat utilization heat exchanger operate at nominal conditions, because constant temperature goes from the hot, constant temperature goes from the cold. So in the steady state operation, just the level in the tanks are changing, but not the temperatures. A modification of the two tank system is single tank with thermostratification, so-called thermocline. It can be achieved either in solid beds, for example gravel beds, where between the gravel flows, for example, air, or it can be achieved with liquids, where if the liquid is not mixing too much, so you can see that we can achieve a very sharp temperature drop between the discharged part of the tank, where we have here temperature, let's say about 180 degrees C, and then the charged tank is at 300 degrees C. And this temperature, like separating zone here between the height between 2 meters and 5 meters from the top, or 2 meters and 6 meters from the top, is this called thermocline zone, and is basically some kind of buffer between the hot and cold zone. And if we can achieve it, so we are good with just a single tank. That means saved space and mostly save capital costs. Then the second option is non-stratified tank, which works more like just a buffer, which temperature is changing during both charging and discharging. So as you have the mixing of the fluid at certain temperature, while the high temperature goes in, so of course it's some exergy loss, and as this tank is changing in temperature, so the operation is definitely non-steady. So the tank at temperature Ts, what comes in is the fluid at collector outlet temperature, so this temperature is increasing, while the temperature of the tank is the temperature over here going back to the collector. And when we want to have the load, so we have some return cold water from the load, which is cooling down the tank, and again the temperature at the tank is the temperature that goes to the load. If the load would not allow temperatures beyond certain points, so we could have some additional mixing of the return water or return fluid into the tank output. So lots of disadvantages, but why do we do this? Basically because it's simple and cheap. And also in especially domestic applications, the operation of the tank is something between the stratified tank and non-stratified. Still, the higher temperature should be at the top, the lower temperature should be at the bottom, but the stratification is definitely not that nice as we have seen over here, but some temperature difference is present. And now we go to our calculation example, where we compare hot water storage systems based on system with single tank at single temperature and two tank system. And the boundary conditions that we have are the heat source of 95 degrees C. We want the storage system to be able to provide peak demand of 100 kilowatts over the course of 2.5 hours. And we will also have a look at two different heat demand temperatures, where in the first case it would be system going between 85 to 55 degrees C, and the second system would be representing some low temperature heating system, for example with just floor heating, 55 to 35 degrees C. In order to calculate the parameters of the storage systems, let's start with the boundary conditions, which is the heat source temperature, 95 degrees C. Then we will have the temperature difference in case that there would be some intermediate heat exchangers between, let's say, the source and the tank fluid, or the tank and further on. But at first we will put 0 degrees. Now the demand thermal output, and for simplicity we will say that also it's the same amount of power that is available for the charging, which was 100 kilowatts, and the time of the required thermal energy demand was 2.5 hours. So first of all, the amount of the energy is the power output multiplied by the time, and we will get, you can obviously see, kilowatts multiplied by hours are kilowatt hours. So the demand in energy is demand time multiplied by the charging output, and it's 250 kilowatt hours. But instead of kilowatt hours, it is more comfortable to calculate with kilojoules. So 1 watt hour is 3600 watt seconds. So 1 kilowatt hour is 3600 kilowatt seconds, and kilowatt second is kilojoule. Or eventually you can see that this is 900 megajoules of heat. And now let's go for the different cases of storage systems. So we will have heating temperature, for the hot output, hot required temperature for the heating, and then cold return from the heating. And we will have the case high temperature heating and low temperature heating. The high temperature heating had required temperature 85 degrees C and it cooled it down to 55, while the low temperature heating system required 55 degrees C and the return temperature was 35 degrees C. So these were also our inputs. And now we will start with now we will put in the temperatures in the tanks, where we will start with the mixing tank. So when the mixing tank is charged, its temperature is the temperature of the heat source, eventually minus some temperature difference on some heat exchanger, if it would be present. Here in the simplified system scheme over here, the heat source fluid goes directly into the tank, so there would be no temperature difference like this, but we will see what would happen later on if it was there. So it's charged, and now the temperature of the tank when it's discharged. So we are using let's say it's hot water, so we are using the hot water all the way up to the point where we can utilize it. If it drops below the required temperature of 85 degrees C, we could not utilize it anymore. But if we again had some heat exchanger in between, so it's not the temperature of the heating demand, but it needs to be a little bit higher if there was the temperature difference. So we can now put here, for example, 1, and we would see that if there was 1 temperature difference on some heat exchanger at both ends of the heat exchanger, so the charged fluid temperature in the tank is 94 degrees C, 1 degree less than the heat source, while the tank is considered as discharged when it no longer can supply the heat for the utilization, which is the required heat for the utilization, 85 degrees C, plus the temperature difference, so 86. Now we can log the values which were common for all the cases. And we can also extend this to the low temperature case, where again the charged tank is at the temperature at the heat source, or eventually lower by some minimum temperature difference, and the discharged temperature of the tank is the required temperature of the heating plus eventually some temperature difference. Now we can change it back to 0. And we can calculate what is the mass of the, if it's water, so what is the mass of the water required for the supplying of this amount of energy, 250 kilowatt hours. But in order to do that, we will need some thermodynamic parameters. So let's say that the storage fluid is indeed a water at pressure at 2 bars, which is 2 times 100 1000 pascals. And for simplicity, some mean temperature, let's say about 70 degrees C, and 70 plus 273.15, and we get the temperature in kelvins. And what will we require is the specific heat capacity, Cp. So we will use function props Si, where we want to get the specific heat capacity, so it's C based on pressure, temperature, and the working fluid is water. And this is in joules per kilogram and Kelvin, and we are calculating here with kilowatts and kilojoules, so divided by 1000 and we get kilojoules per kilogram and Kelvin. And also later we will calculate volume, so we will need density. And we can use basically the same function. Just we switch the C into D as density, and we get kilograms per cubic meters. So now the mass of the required water in the storage tank. Well, you definitely know the calorimetric equation. Q is mc delta T. So from this, if we know the temperature of the charged and discharged tank, the average specific heat capacity, we can get the mass. So it's the heat in kilojoules divided by Cp and temperature difference charged minus discharged tank. Let's also look the parameters common for both cases, and get the brackets divided by this whole, yes, like this. So we get value of 21,000 kilograms. Now what happens for the low temperature case? Since we have much larger temperature difference, so there we need just quarter of that, 5,000 kilograms. Now from this we can get the volume of the tank, which is nothing but the mass of the tank divided by the density. And we can see that for the first case, if we have just mixing tank operating between 95 and 85 degrees C, which is not much, so for the required amount of heat we would need 22 cubic meters, while for the second case we would need 5.5 cubic meters. Now from this you could, for example, convert it to cylinder with given diameter and height for actual sizing of the component. But what we will have a look at now is what is the mass flow rate of the water during charging. When we want to have also 100 kilowatts of charging power and we want to, the tank is discharged, so what is the required mass flow rate? So So how to get it? Basically similar equation as here, just it would be heat flow, it would be heat power in kilowatts, so Q dot, and we would get kilograms per second, so also instead of the mass we get m dot over here. So it is the charging power, 100 kilowatts, divided by Cp times temperature difference of the charged tank and discharged tank, and we get 2.4 kilograms per second. If we have actually the constant charging power, charging load, so what would happen as the temperature of the tank would be increasing? So from discharged, let's say 85, it would go to half charged to 90. So suddenly the mass flow rate would need to be significantly higher, almost 5 kilograms per second. That's the non-steady regime of operation of the tank and its temperature. So you can see how the mass flow rate would be actually changing, and it's here relatively high. Let's reference this again and use the same for the low temperature system, where during the charging we need 0.6 kilograms per second. Here during charging, let's say when it goes to temperature 70, so again for the same load, same power, 100 kilowatts, the mass flow rate would need to get higher. But it's not that high as in the first case. And now similarly, let's have the same for discharging, where for the discharging again we have 100 kilowatts, the specific heat capacity, but now the temperature difference going to utilization, it's the charged temperature minus temperature difference. So let's say like this, minus, and what is returning is the cold temperature from the heat source, from the heat utilization, eventually further lowered by also the temperature difference. And the last overall bracket in the end, and we get that for the discharging we would require 0.6 kilograms per second, and this is in the case when the tank is charged. If it would be discharged, so right before depleting its capacity, it would go from 0.6 that we had from charged to 0.8 that will be in the discharged state. And we can have same for the low temperature tank. So again 100 kilowatts going between the 35 degrees CS return and the required temperature is 55. So in order to get the 100 kilowatts of heat, we would get 1.2 kilograms per second in the when the tank is discharged, when it would be charged, so just 0.4. So you can see how the mass flow rate needs to be actually changing in order to get the constant power output. One possibility for the discharging case is that the mass flow rate would not be changing, it would be at these higher values, and here it would be a shortcut with the freeway valve that would mix some of the return temperature back to the outlet to the heating to have it at the constant 55 degrees C. Now let's go for the two tank system. So this was the mixing tank. Now two tank, or same with single tank or with thermocline. So in the charged state, the temperature is the temperature of the heat source minus the temperature difference. In the discharged state, it's the temperature of the return from the heat from the utilization over here. Eventually, if there would be heat exchangers, so the return temperature would not cool it down that much. So plus the temperature difference. So let's reference what stays the same and extend this also to the low temperature case. So also in the low temperature case, the charged would be 95 and discharged would be with 0 degrees temperature difference at 35. Now what is the mass of the fluid in the tank, or in actually both tanks, either one tank or second tank, or part and part? So it's the thermal capacity, 900 megajoules, divided by specific heat capacity times temperature difference between charged and discharged states. So here we have 5.3 tons, and in the second case just 3.6 tons. So you can already see the change from the previous case. And we can immediately put under that the volume of the tank, where in the first case we have 5.5 cubic meters and in the second case 3.7. And now get the mass flow rates. So during charging, it's the charging heat power divided by Cp and temperature difference between charged and discharged. .6 kilograms per second. And during the discharging, so again it's discharging heat divided by specific heat capacity times, and now it's just going between the same temperatures in the tank, so temperature of the charged and discharged. So you can see that it's the same value. And let's see the small tank, where regardless of the state of charge, also we have the same mass flow rate during charging or discharging for the same power, and regardless of state of charge, if it's full or empty, still it's just the water level that is changing in the two tanks, and the mass flow rate remains the same, so the operation of all the system is at steady state. And now let's just see what would happen if we would have 2 degrees temperature difference. So in the single mixing tank, suddenly the volumes of the tank increased quite a lot, from 22 to 36 and from 5.5 to 6.1 cubic meters. Also, the required mass flow rates increased quite a lot. You can see, especially in the for the high temperature case, if we have the large temperature difference, so the mass flow rates did not increase that much, and for the discharging they are quite similar. Now for the case of the two tanks. So again, the change in the mass flow rate or the overall volume, or especially here the change in the mass flow rate and the overall volume, is not that dramatic, and everything stays at steady state regardless of the state of charge. So for basically most of the applications where the larger periods of storage time and efficiency is, especially like exergy efficiency of the system is required, so the system with the two tanks is more beneficial. Now let's have a look at the methods for electricity storage. So you can see various methods for storing electricity at the graphs over here, where on the x-axis we have the power rating, the power in watts, kilowatts, or up to even gigawatts, and in the y-axis we have the storage time, or rather discharge time of the storage, going from seconds to hours, or in the second chart even to eventually days and weeks. So you can see that for the lowest power output and very short times of the discharge are suitable systems as flywheels or supercapacitors, eventually magnetoelectric storage systems. Then for the time going, let's say from small to large amount of minutes, we are having various types of electrochemical batteries, typically known in the past as the nickel batteries, up to Li-ion batteries and some modern batteries, followed by, in the period of hours, by flow batteries. We can see that also here on the right side, the very left and bottom part, supercapacitor, then eventually some flywheels, then is the area of solid state batteries, flow batteries, and then for the very highest power outputs and also largest duration of the discharging are the methods as the pumped hydro, eventually power to fuels, as we have here hydrogen or methane. We have pumped hydro on the left graph over here. Power to fuels, well, depends what are the capacities, if we convert it just in the fuel cells, or also if we convert it back to electricity in some power plant, so it would go into really high power systems, into high power rating. systems as compressed air energy storage, and systems of storing electricity as a heat, electric thermal energy storage, or also known as Carnot batteries, power to heat to power. And now we will have a look at calculation example for battery storage system, where the task is to choose suitable batteries for electricity storage systems, where the batteries would be having a voltage of 360 volts in nominal. That means 100 batteries in series for typical lithium batteries, where the nominal voltage is 3.6 volts per cell, and the capacity of single battery cell would be 2550 milliampere hours. And the parameters of the storage system would be for two cases. First case, having 2 hours of storage with the power rating 5 kilowatts, and the second, shorter duration, half-hour storage with the required power rating of 10 kilowatts. And the last thing for the calculation, most of the batteries have limit on the discharge rate 1C, one capacity of the battery. If we discharge it in higher rate, so that means that the battery life would decrease dramatically. So the parameters of the battery storage are that single cell has the capacity of 2550 milliampere hours, which is 2.5 ampere hours. That means the battery can be discharged by the current 2.55 amperes for the period of 1 hour. Then the voltage of the whole battery pack was nominally 360 volts. The required storage capacity was 2 hours, or discharge capacity, discharge duration. So it's 2 hours. And the power rating was, in this first case, 5 kilowatts. So let's put it like this. We have again two cases, case 1 and 2, where in the first case we have 2 hours in 5 kilowatts, and the second case was just half hour with the power rating of 10 kilowatts. So now what is the required energy in the battery? So it's the discharge duration multiplied by the power, and we get kilowatt hours. So the first case requires 10 kilowatt hours, second case requires 5 kilowatt hours. Also we can convert it to kilojoules. And now what is the discharge current? So we know that the power is voltage times the current. and we know the discharge power, the power rating 5 kilowatts. We know the voltage, so we can get current from that. So this is 5000 watts divided by the voltage, and we get current in amperes. So we can see the first case, the current drawn from the battery pack is almost 14 amperes, in the second case 28 amperes. Now what is the required battery capacity? Where the capacity is measured in ampere hours. So we have the current, we have the duration of the discharge, ampere times hours, we get ampere hours. So we have the result that the battery capacity would be, in the first case, 28 ampere hours, in the second case about 14. But before we calculate the number of battery cells, let's have a look at the discharge rate. Because we have the current divided by capacity, and we get the discharge rate being 0.5 capacity in the first case, so that's less than 1C, so that's alright. But in the second case, the discharge rate is 2 capacities, so either we have some batteries that are built for higher discharge rates, we would need to increase the capacity to double to be at the 1C. So what we can actually do, we will say that the battery pack will provide the double storage period from half hour 1 hour, and we are at the 1C. And we can see that actually in this case we have the same required capacity of the battery. And the last thing, number of battery cells. We have the battery capacity divided by capacity of a single cell, where the single cell we need to convert the milliampere hours to ampere hours. So like this. And we get a result that we will need 11 parallel cells of this battery type with since one battery has 3.6 volts, so 100 cells in series. So the battery type or battery configuration in case of lithium-ion batteries would be 100 batteries in series and 11 batteries in parallel for both cases, if the maximum discharge rate is 1C. The last topic of this tutorial is focusing on diagrams of performance duration and sizing of source capacity or source power. So this will answer the question of how many and how big sources are required to be chosen, and what will be the energy production and fuel consumption over a period of, let's say, 1 year. So during the day, over the course of the day, the thermal load of basically any heat demand is typically changing. So what you can see here is the typical daily heat demand diagram for some residential area or residential application, where you have some baseline for, let's say, tempering the house. Then in the morning, where some life in the house or houses begins, so you have demand for more heat, especially due to utility hot water. That goes to the noon, then some decrease, and then during the evening again increase before the end of the day. Then let's have a look at example of typical heat demand diagram for example, schools, where you have again some baseline for tempering the building. Then in the beginning, when in the early morning, when the operation starts, people come in, they need hot water, they want to increase the temperature in the rooms, so suddenly everything goes up. The same basically type of utilization and required heat is more or less constant or just slightly decreasing during the day, as typically the outdoor temperature is getting higher. And then when the pupils and employee of the school leave, so again there is sharp decrease in the heat demand back to some base load. And in the industry, where there is more or less constant demand for the heat, but there is two-shift industry, so during the night time the machines are being shut down. Then in the early morning there is steep increase, more or less constant or just slightly decreasing during the day for the heating demands, and then again when everybody switches everything off, so sharp decrease back to the baseline. This heat demand can of course change based on the month of the year. What is seen over here, where we have demand for heating, hot water and losses in the system distributed among different months of the year. So we can see that in winter we have really high heating demand, then the amount of the required hot water is lower, and then there is some share of the losses. As we are moving towards the summer, so the heating demand goes lower up to the point where heating is no longer required over the summer, and there is just required hot water, and there are some losses in the system. And then again, as the heating season starts, so there again start to be demand for the heating, and also in winter there is a little bit higher consumption of the hot water than in the summer. Now if we take the required capacity or required thermal power or thermal load in the heat and order it from the highest to lowest, so we get a curve that looks somewhat like this. So these are the values that are here, let's say with the resolution of a day, but these days are ordered and sorted from the highest thermal load or highest heat demand to the lowest one. And we can see the requirement for heating, which over the course of the year, going to 8,760 hours, is decreasing up to the point where there is switching point between the heating season and summer season. The hot water is needed throughout the whole year, just a little bit less during the summer, and also the losses in the system are present, where in the summer you are just using the systems for hot water, typically being at constant temperature, so the losses are more or less constant. In the heating season, at the beginning of the heating season, the losses are relatively higher because all of the system is at higher temperature, but you don't need that much of the heat. While in the highest heat demand, the absolute value of losses is a little bit higher, but the relative value of the loss is much smaller. So the same curve, just shown with some specific periods of the time. So we have the heating season, then the summer season, and typically there is some period for maintenance. Then if you would take the maximum thermal load and convert the area under the curve into a rectangle, so you would get a period which is called utilization of the maximum power, which is the period of how long this maximum heat demand would be supplied over the year to cover all the heat required. And also we can see some minimum necessary heat input, which basically covers the utility, hot water and thermal losses at the summer with the lowest demand. Now some typical diagrams of these curves for residential and communal sector, where the curve is, or the diagram is rather sharp, where we can see some period of the coldest winter where you have the highest heat demand, and then dropping relatively sharply to summer where you need just to provide the hot water. And then, for example, for some industry, there is some base load heat demand which is rather constant for the most of the year, let's say for some industrial processes, and then just on top of it is superposed what is needed during the seasonal change and for the heating. So the shape of this load demand curve is not much less steep, much less sharp. Now we are going to the issue of sizing of the energy sources. So basically we need to provide the heat in the area under this curve, and we need to respect the parameters of the heat sources, which is some minimum and maximum load. So typically what you can do is to design some base load system which would run at the constant power all year round, and then you would have some different system, eventually peaking system, which would provide just the heat in the shorter period of time. In residential applications, you're typically trying to provide all of this with just single piece of equipment, and then it's kind of troublesome to cover the lowest demand in the summer. So there is cycling operation of this system, and usually some thermal storage is suitable. So when we are sizing the heat sources, and when we have the dispatchable heat sources, so we should respect the output range. So for example, for the gas boilers, they are controllable pretty well from, let's say, about 20% to 100 or 105% of the thermal power output. If you have boilers for biomass or coal, so their operating range is smaller, let's say from about 50%. Microturbines, let's say from about 60%. The combined heat and power units based on internal combustion engine can go typically down to about 40%. but some micro-cogeneration systems like Stirling engine or fuel cells units, they are typically designed to run only on the 100% power output. So they are good to be the base load systems which run all year round, which are operational the all year round. And then lastly we have here a heat pump, where it's important to note that the parameters and the performance will also change with the temperature of the heat source, especially if it's air to water or air to something. So as the outside air temperature would be decreasing, the coefficient of performance of the heat pump will also decrease. But the typical range of power output, let's say 60 to 100%. And what is important to note is that when we are running any of these heat sources for part load, so it will always be associated with decrease in efficiency. Now what if we have some intermittent sources or maybe some auxiliary systems? So the types of equipment like this are accumulation systems, solar systems, eventually some other renewables, and of course the external sourcing when it's possible from power or thermal grid, and that is kind of a backup that is always there, just you need to pay for it. So for sizing of these sources, it is necessary to know the time distribution, not just the overall balance in the overall heat demand curve, and you need to know what is the power production or energy production and energy consumption at different periods. And now we will go for an example where we will have given diagram of the heat demand duration, and the question will be how many resources or how many thermal sources and how large to implement. And the questions will be how much heat and electricity will be produced and how much fuel will be consumed, when we will consider two options. First, using only gas boilers, least amount of them possible, and second option, having some combined heat and power system, either based on internal combustion engine or micro turbine, and gas boilers for peaking, and also we would have some thermal storage available. And the diagram is over here. So on the y-axis we have the required power output, the thermal output in kilowatts, and on the x-axis we have the duration of the year from 0 to 8,000 hours, where we assume the rest to be left for maintenance, and there the system would be shut down. So what we can do with the resources is, for example, say that we would have 20 kilowatts boiler, which can be easily regulated to its 20% of thermal output, and we would have the 20 kilowatts boiler running to full power all the way to this point, and then going to 50% of the thermal output for the rest of the year. So this would be energy supplied by, this would be the heat supplied by the first boiler, let's call it boiler 1, and then we have remaining 80 kilowatts, which could be covered by the second boiler. where for a very short period of the year it will be running at the full power, and then the power output would be decreasing as the heat load is decreasing all the way to 20 kilowatts over here. It's 20 kilowatts, here would be the 80 kilowatts. So this is 25% of the power output, but only for a very short period of time. So this is one possibility. Other possibility is that the small boiler would be just 10 kilowatts. Basically the amount of possibilities is infinite, but we are just showing some examples. So we would have kilowatts for boiler 1, which would be running full power all year round, and the second boiler would be 90 kilowatts, where here we have at the end of the heating season we have 30 kilowatts of power output, so here it would be running at full power, here it would be running at 1/3. So this is the option. Third option, just for example, you would have still the 10 kilowatts small boiler, which would be running only in this summer period, and then it would be running in the period of the deepest temperature when the heating demand is the highest, and as it's running only in short period of time, so perhaps it could be cheaper, or some repairs and overhauls could be planned for the larger remaining of the year, where most of the companies focusing on maintenance and repairs would have available time, and then the rest would be covered by second boiler, which would be again at having thermal output of 90 kilowatts. So you can see same as here, 10 and 90, but just running in different periods. And the 90 kilowatt boiler would be running in this period. Where again it's running here at 100% of the load, but not for just the shortest period, but for 1000 hours. And then the load is decreasing to 40 kilowatts out of 90, which is 44%, so perhaps it could have better overall efficiency. Here the 10 kilowatts boiler would be running at the full power, so there the efficiency would be also good. And here for this shortest period of time, this would be full power, and basically below it's 20%. That is a really small difference, the 2 kilowatts, where it would be operated, for example, in some cycling regime, on and off every now and then. But in total it's just 500 hours of this cycling operation. And it's not 500 hours of continuous period, but it's 500 hours distributed into the daily power changes, daily output changes. So even though the limit is 20% of the power output, this 2 kilowatts would be definitely covered by the capacity of the distribution system, the piping itself, and during the transfer regimes, and by the cycling of the boiler. So now let's have a look at this specific case. What would be the expected fuel consumption, and what would be the average periods of, and what would be the average power output of each boiler. So the average power output of each boiler, or the amount of heat that is delivered by each boiler, can be determined, let's say for the green one, for the boiler 1, it's running 2000 hours at the full power, which is at 10 kilowatts, plus 1000 hours times half of that on full power and then going to 0, so in average it's 50%. We can say 10 plus 0 divided by 2 as the triangle surface. So the heat provided by the boiler 1 is 25,000 kilowatt hours, 25 megawatt hours, and the average load of this boiler 1 like this would be the heat provided by the boiler 1 divided by the period of its operation. So it's 25,000 kilowatt hours divided by the 2000 plus 1000 hours, so 3000 hours. So it's 8.33 kilowatts, which is 83% of the full load. Now we can do the same for the second boiler. So the heat provided by the boiler 2 is 1000 hours multiplied by the full power, which is 90 kilowatts, plus 1 to 6, that is 5000 hours, multiplied by the average power output, which is 90 plus over over here 40 divided by 2. And that's it. So it's 90,000 in kilowatt hours in the first period plus 325,000 kilowatt hours in the second period. So it is 4015 megawatt hours. And here you can make a check that 4015 for the second boiler plus 25 for the first boiler is 440 kilowatt hours. Megawatt hours, which will be also the area of the whole diagram. So it should be 6,000 hours times the average power output in this period, or average heat demand in this period, which is 100 plus 40 divided by 2. Plus 2000 hours times 10 kilowatts. And we will get that it is indeed 440 megawatt hours. And now let's finish this so we can have the average load. We can also mark it like this for the boiler 2. So it's the heat provided by the boiler 2, 415 megawatt hours, divided by the period of the operation of boiler 2. So this was 415 thousand divided by 6,000 hours. And we will get 69.2 kilowatts. Which is about 77%. Now for the case with the CHP systems. So, for example, one way of applying the heat sources would be to have some base load micro cogeneration system, which would be running basically all year round, with the thermal output of 10 kilowatts. So it would be suitable, for example, for something like the Stirling engine systems. So CHP1. With thermal output of 10 kilowatts. Then we could have, for example, microturbine with nominal power output of 50 kilowatt or 60 kilowatts. That's 60. So it would be running at full power over here. 60 kilowatts, so 70 kilowatts of total thermal output. It would be running for the full power, on the full power, for 3000 hours a year. And then for for the rest of the heating period, which is another 3000 hours, it would be running at part load down to 50% of power output. So it's the CHP2. Now, since we will have some accumulation, so the effect of the accumulation will be most visible in some periods of the highest thermal load. So basically we can say that it will offset this amount of heat into here. And then for the other periods, in case of the cycling of the resource, so for example the lowest power output of the CHP2 would not be 50%, but perhaps it could be again a little bit higher. So basically this amount of heat could be, for example, transferred in here, and therefore the lowest operating point would get from 50% to 66%. So this is how the accumulation works, where the accumulation is only for 10 kilowatts of thermal output, and the storage capacity would however need to be determined from, let's say, daily or weekly diagram of thermal load. It cannot be determined from this summarizing diagram. And the last point would be the peaking boiler, which would need to cover the remaining 20 kilowatts. So if we take it with the accumulation, it would cover this part. Again, in real operation with the accumulation, so here it would not go probably for that much of cycling, but thanks to the accumulation, this period between 2000 and 3000 hours of the year the heat demand from here would get to operating the boiler at higher power output here. So now to get the overall parameters, so let's have two columns for boiler 1 and boiler 2. Where we have the thermal output, for the boiler 1 it was 10 kilowatts and boiler 2 90 kilowatts. Then the provided amount of heat or supplied amount of heat. For the first boiler it was 25 megawatt hours, and for the boiler 2 it was 415 megawatt hours. Now we have the average power output, which was, for the boiler 1 it was 8.33 kilowatts, and for the second one it was 69.2, and the amount or the period of the operation for the boiler 1 it was 3000 hours, and for the second boiler or boiler 2 it was 6000 hours. And maybe lastly, also the average load, which in the case of the boiler 1 was 83% and boiler 2 77%. So based on this average load, we can assume what would be the average operational efficiency of these boilers, since these are gas boilers running at a relatively high average load, 83 down to 77%. So we can assume that the efficiency of the boilers could be quite high. Let's say that in both cases it will be 95%. So now, when we have the operational efficiency and the supplied heat, we can get the required heat input in fuel, which is the supplied heat divided by the boiler efficiency. So it's supplied heat in the kilowatt hours, or we can have a look at the megawatt hours. Also in megajoules. Or maybe rather let's have gigajoules. And lastly, if the natural gas would have the heating value of 33.5 megajoules per normal cubic meter, so we can also get the amount of the fuel as normal cubic meters. And now, since both boilers have same efficiency, well, maybe the smaller boiler would not be having that much, let's say just 90%. So now let's have a look at the overall parameters. So the fuel input in megawatt hours would be just sum of these two, 464 megawatt hours. The supplied heat, which we also calculated previously as 440 megawatt hours, needs to be also the sum of these two. And now let's have it as megawatt hours. So we can get the average efficiency of the boilers of the whole boilers in the whole system as Q supplied divided by the heat in the fuel, and we will see that as most of the heat is provided by the large boiler with high efficiency, so we are just very slightly under the 95%, where the 95% is the big boiler. Okay, so with that we have some overall parameters for the case with the boiler with the two natural gas boilers. And now let's go for the case with the CHP systems. So here we have the CHP1, CHP2 and the boiler. The accumulation we will assume for simplicity that it has no losses, so it does not produce anything nor lose anything. Now the operating hours, the operating period in a year, or well, let's copy the values from the top. Let's see how it will fit. So for the CHP1, the thermal output was 10 kilowatts, and right under it let's have a look electrical output, which for some well-tuned system like this could be perhaps something like 2.5 kilowatts, but actually let's get to it later. The second CHP unit had 60 kilowatts of thermal output, and the boiler had 20 kilowatts of thermal output. Now the supplied heat. For the first CHP, it was the 10 kilowatts times the period of operation times the average load. So let's order it like this. The period of operation 8,000 hours. For the CHP2 it was 6,000 hours. And lastly, for the biomass boiler, let's consider the cases with all the accumulations that we have illustrated. So 2,500, 2,500 hours. Now the average load in kilowatts. Let's have it like this. So for the CHP1, it was all the time running at the 10 kilowatts, so there nothing is changing. The CHP2 is running for 3000 hours at the full power. Hours times the full power of 60 kilowatts plus, and then 3000 hours times the power output of 60 plus 30 kilowatts divided by 2, and this divided by the whole operating period of 6000 hours. So it's 52.5 kilowatts in thermal in average. And lastly, the boiler, it is running for 2000 hours at the full load, 20 kilowatts plus 500 hours at the half load, so 20 divided by 2, and the total operating time 2500 hours. So this can be already referenced in here. And these can be considered as the inputs. And this can be also times 10 as the amount of heat divided by the let's just keep the 10 here like this. Okay, so we have the average load. In the average load we actually already had the amount of the heat supplied, but let's just check that it's valid also as the average load times the period of the operation, and let's have megawatt hours. So you can copy the same function into the next cells. And we can quickly check that the sum of these three is 440 megawatt hours. So it was the supplied heat. Now let's have a look at the average load. Which is the Q dot average divided by Q dot thermal. So also thanks to the accumulation and desensitizing, so in average throughout the whole year the CHP1 is running all the time at 100%, CHP2 at 88%, and the boiler at 90%. So now let's have a look at the operational efficiencies. Let's call it beta thermal and beta electrical, where for the CHP1 let's say that it's some what could it be, something like Stirling engine or something like that, with the 25% of the average electrical efficiency and maybe 70% of the average thermal efficiency. Now the CHP2 could be perhaps some microturbine with already not running always at 100%, so the average thermal efficiency, let's say 65, and average electrical efficiency, let's say 28%. And lastly, we have the boiler for just some peak operation, so it does not need to be that good boiler. So we would say that the thermal efficiency would be in average 85%, and of course electrical efficiency is 0. It's just the boiler. Actually, it would consume a little bit of electricity for its operation. So now let's have a look at the amount of heat in the fuel. So we have the produced amount of heat in megawatt hours divided by thermal efficiency, and we will get megawatt hours of fuel, or we can again have cubic meters or megajoules. So first let's have the megajoules. Or normal cubic meters as megajoules divided by the volumetric heating value. And let's also have the total values. Let's put it as the last column in here. So it makes sense here in the supplied heat to check that it's 440 megawatt hours, and here in the fuel consumption, where in order to have the 440 megawatt hours you would need 650 megawatt hours of heat. Now when we have the heat input, we can also get the electrical production. So the electricity produced is the energy in the fuel multiplied by the electrical efficiency of the systems. So the small CHP unit provides 28, almost 29 megawatt hours of electricity, the big one 136, and the boiler of course nothing. So this system in overall will produce during a year 164 megawatt hours of electricity for 440 megawatt hours of heat, and it will consume 650 megawatt hours of fuel. So we actually don't need this, but now as the last point, let's have a look at the average efficiency of the system. So let's have average efficiency of producing heat, producing electricity, and combined heat and power production. So the average efficiency of producing heat is the supplied heat divided by the heat in the fuel. Now the average electrical efficiency is the produced electricity divided by the heat in the fuel. And lastly, we have the efficiency of combined heat and power production, which can be just sum of these two, or the same value needs to be also obtained as the electricity produced plus the heat produced divided by the heat content in the fuel. So we can see the average efficiency for thermal production 68%, electricity just above 25%, and combined heat and power 93%, which is quite nice because here the sizing went pretty well. If the sizing would not be done properly and if there would be lots of frequent startups and shutdowns, so the average efficiencies both for electricity and thermal production could go significantly lower, and therefore also the overall efficiencies would go lower. Let's have a look what would happen if just the electrical efficiency dropped to 20%. Let's say this one can stay at 25%, but this one would drop to 20%. So suddenly you have the electrical efficiency overall below 20, and you produce significantly less amount of the electricity. If also the efficiency of the CHP units went lower, let's say 55, 60, so you can see how the heat input would change from 650 to 760 megawatt hours. So let's put it back. And let's compare the application of the CHP system and accumulation compared to just the natural gas boilers. So here we had in a year consumed only 465 megawatt hours of heat in the fuel, and we provided the heat that we required. Here with the CHP we consumed significantly more than 40% increase in the fuel consumption, but in return we got some electricity, specifically here 164 megawatt hours. And this is the end of this tutorial.